Thank you. Very happy to be here. Happy to see you all here. So what I want to talk today are the observations of spectral lines which are formed via scattering, which means in the solar upper photosphere and chromosphere, and the interpretation of the observations of these lines which have very high spatial resolution and very high spectral resolution. So I will show you this data in multiple forms on multiple occasions today, and we will discuss them and we will see what we can learn from them. But first I want to spend significant amount of time on discussing what are inversions, how do they work, why are spectral lines important, how are they formed, and what happens there. So I hope that even if you're super familiar with all these things, you still get to learn something new. And in specifically the lines that I want to talk about today, and this is the mean solar spectrum, so basically what we know as Atlas, right? The spectrum of the sun as a star, more or less. And the lines that I will talk about the most today are these two lines here, and these are sodium D1 and D2 spectral lines. So they are particularly interesting for us because they are the true example of what we would call non-LTE lines, which means that they are dominated by scattering. And you can immediately see that by the fact that their cores are very, very, very deep. So what we usually see in the lines that are formed in the lower layers of the solar atmosphere is that no matter how strong the line is, it never goes too deep because it cannot go too deep. Because contrary to what we are naively taught when we are undergrads, that the lines are simply formed by absorption, there is also emission in spectral lines. And in principle, line core will always be formed somewhere, and it will give us information about that layer of the atmosphere. And if the line is in LTE, it will never be so strong. However, in scattering-dominated lines, the photons escape outside of the solar atmosphere. And for some reason, the emission in these lines is much, much, much lower. And then we see lines which are so deep, like this. However, it creates many problems. It's not that these lines are super useful or super advantageous for anything. Actually, why I'm studying them here is I'm just using them as an illustration of non-LTE lines. Non-LTE gives you much more problems than benefits. But sometimes we are just doomed, and we have to do it. Right. I just want to stress that sun is super special for us, although I'm sure that you already know it. And here there are some very simple calculations. And basically what I wanted to say here is that if you use the biggest telescope today, which would be something like 10 meters diameter, right? And you observe that 500 nanometers, this would be your theoretical spatial resolution. But still you won't be able to resolve the sun at the distance of 1 parsec. So it would still be just a point for you. However, if you use the biggest solar telescope today, which is Gregor, and you observe at 500 nanometers, theoretical spectral resolution equates to something like 60 kilometers at the solar surface. So 60 kilometers is very small. And you can see here how much details we can see today. And it obviously makes sun very special object to study, right? Because we can see things resolved. We see the atmosphere resolved, and somehow we hope, and basically high resolution spectropolarimetry gives us ability to analyze each of the pixels in this image separately and to get sort of a 3D structure of the solar atmosphere. Of course, this is not as simple as it sounds, and it's not straightforward as it sounds. It's not like you observe and you get things straight away. Not even in medicine we get to do this tomography to get unique images of things. And here there is a lot of degeneracies underneath. And what I want to talk today is how hard it is to interpret spectropolarimetric observations of this kind. So in principle, what we work with, and I apologize for the poor quality of video, it's because I made it. So if Michiel actually made it, I'm sure it would be nicer. So this is a small piece of the atmosphere. So few arc seconds times maybe 20 arc seconds here. And what you see in the upper panel is the intensity. And here in this lowest panel here, you can see how we are scanning through the wavelengths. And you can see how the image here is changing. And this is the main paradigm, if you want, about the analysis of spectral lines. And that is that as we look at different wavelengths, the sun looks different. And the reason for that is that by looking at different wavelengths, we are sampling the different layers of the solar atmosphere. And something that is relatively commonly seen is that if you look at the continuum, what we are going to see is so let's wait a few seconds. So what we see now is more or less the granulation pattern. But then you will see as we get close to the cores of the lines, we're going to see this plage very nicely. We're going to see inverse granulation. And then when we hit exactly the corners of the lines, we see something which you could say we are looking at the temperature minimum or we are looking at the chromosphere. That's something that we can discuss. But another thing that carries a lot of information is the middle panel here, and that is where I'm plotting the circular polarization in the line. And we know that because of the Zeeman effect, the polarization there is polarization in spectral lines, and this circular polarization here more or less maps where the magnetic field is. And not surprisingly, the position where the signal, where there is signal in Stokes V more or less overlaps with the position of plage that we see here. And another thing that I want to stress here is that additionally to those two very prominent spectral lines here, which are sodium D1 and D2, there are these two apparently insignificant lines. This very small one here is a neutral iron line. This slightly stronger one is neutral nickel line. But if you look very carefully at the circular polarization image in these lines, you see that they also carry signal there. And it is very important for us because these lines are obviously much weaker, which means that opacity there is much smaller, which means that they sample much lower layers of the solar atmosphere. And by looking at this combination of the spectral lines, we somehow get some idea about in this specific case, what I want to stress is that we will get the depth information on the magnetic field. So simply saying, we could say that these two carry information about the magnetic field in the lower photosphere, and the sodium lines carry information about the magnetic field in the, let's say, upper photosphere temperature minimum kind of thing. So now I want to spend some time talking about how we can actually infer the physical quantities from here. And for that, we need to answer two questions. One question is, how are the spectral lines formed and what they actually are? And the second question is, why are the spectral lines sensitive to the magnetic field? Okay? Or why is the radiation in spectral lines polarized? Today, I will focus mostly on Zeeman effect, but there is another super interesting, super complicated also, but also effect with a lot of potential, and that is Hanle effect, which acts in these scattering dominated lines. And actually, specifically D1 and D2 lines of sodium are very interested from the aspect of a Hanle effect, but now we are talking about much stronger magnetic fields where Zeeman effect is much stronger. So small refresher on the spectral line formation. We get spectral lines because there are bound transitions in the atoms. And the key quantities that appear here and that we basically need to calculate if we want to model formation of the spectral lines are the emissivity and the opacity in the spectral line. And then another two key quantities which we need to calculate these are what we usually call level populations of the levels involved in the spectral line formation. Right. So to really model a line, you need to calculate these level populations at each depth in the solar atmosphere, calculate opacity and emissivity, and then put them into something called radiative transfer equation, and the solution of that radiative transfer equation gives you the emergent spectrum. But simply speaking, the spectral lines are important for the following reason. The opacity in the spectral line changes by a factor of many over a very small spectral region. So for really strong spectral lines, for example, Lyman alpha, the difference between opacity in the continuum and opacity in the core of the line can be millions or even billions. So it's really, really huge difference. And I remind you now that our paradigm is that when we look at different opacities, when we look at different wavelengths, there are different opacities there and we see different layers of the atmosphere. Or you could say that when you look in the core of the line, you see more shallow layers, and when you look in the wings of the line or in the continuum, you see deeper layers. So then by just looking at a small chunk of the spectra, we get information over the range of wavelengths. And we are somehow trying to exploit that. Okay. So in principle, in case of the lines which are formed in so-called local thermodynamic equilibrium, things would be relatively simple, and we know very well how to do this. So you basically start from a model atmosphere, and what I have here is a piece of Murray simulation, and here are the temperature and the line of sight velocity in the solar photosphere, right? And then I have for all these pixels here, temperature, pressure, velocity, etc. I use these to calculate the level populations. I calculate emissivity and opacity, and I get the spectra. And here you can see that different pixels of the simulation will result in a different spectra. But this spectra doesn't only depend on this layer here. It also picks up the information about the all other layers. So basically, I'm also picking, let's say, things from the upper photosphere. Here I'm plotting some completely different lines. So these are infrared lines of iron, which are the very, very, very much LTE lines. But this is like the simplest situation that you might have. However, what I want to talk here are the lines which are sensitive to much higher layers of the solar atmosphere. And basically the question now arises, and it's what happens when we are not in LTE. So LTE is basically a very useful approximation, and it says that locally in each point in the atmosphere, matter and matter is in a sort of is in equilibrium, and it only depends on the local quantities. So if I know local pressure and local temperature, I can basically completely describe the state of my gas. I know what is my ionization state, what is the velocity distribution, what are the excitation states, etc., etc. However, as we move up in the solar atmosphere and we reach more dilute layers, which means chromosphere, this approximation is no longer valid. And the reason for that is that LTE is basically established by the collisional processes. As you move toward more and more dilute medium, these collisional processes are more and more rare, and eventually radiative and collisional processes start competing. And at some point, and the point with radiative processes is that they're not local. So if I take, for example, very cold gas and I illuminate it with the radiation, I can ionize or excite it as I wish, but its ionization or excitation state, it doesn't depend on local quantities anymore. And in a way, that happens in the solar atmosphere as well. And when the medium becomes transparent enough and dilute enough, the radiation from one part of the atmosphere can influence the ionization and excitation state in the other ones. And that's basically non-LTE. And if you put it in sort of equations, it looks something like this. We need to replace the Saha equation, Saha-Boltzmann basically statistics. We replace it with something called statistical equilibrium equation. And that is basically assumption that at least the level populations will be constant over in time, and their populations are solution of this linear system here, where we have the competition of radiative and collisional processes. But I mean, the equations here are not so important. What is important is that there is coupling between the radiation field and thermodynamics. So before, in this example here, I just needed to know my temperature and pressure, and I can immediately calculate the spectra. In non-LTE, things are much more complicated because both of these things influence each other. They are coupled. In order to calculate my intensity, I need to know my level populations and the ionization state of the gas, but the level populations and the ionization state are determined by the radiation. And then again, this is not some super big problem. People dealt with this over time more and more efficiently, and now we have very efficient numerical methods to deal with this, and we can solve the problem. And here is a small quiz just to remind you, like, in which sort of objects or regimes we expect non-LTE or LTE. And here we have prominences which would be extremely non-LTE objects. Like the amount of radiation for prominences, all the radiation that we get for prominences is basically the radiation from the photosphere which is scattered on them. So the emission of prominences is completely governed by the incoming radiation. On the contrary, when you look at the granulation, for example, in the continuum, it's very LTE. Where you have the bright structures, that's where the temperature is higher. Where you have dark structures, the temperature is lower. As simple as that. However, some spectral lines, in this case I'm showing H alpha, now you would expect that it's something in between these two things, but now what we think, and what is most probably true, is that H alpha is even more complicated than non-LTE, because this assumption here of the statistical equilibrium is probably not valid. So H alpha is formed so high and in such conditions that basically things are also time dependent. So we really need to use very, very sophisticated things, and that's why very often all the interpretation of the observed H alpha profiles that you see are going to be super basic. So people look at the profile and say, okay, it's wider here, it's more narrow here, the line center velocity is here or there. You can't really invert it, as we would say. And now the question comes, what is actually inversion? But before that, I just want to say a little bit more about the non-LTE. And actually, one of the nicer illustrations of non-LTE is the cover of Rob Rutten's book, which was actually a poster for this famous radiative transfer school in Oslo, where I was still a little kid. And basically, non-LTE is exactly this, that as you're going toward the higher layers of the atmosphere, the photons are escaping more and more. And because the excitation of your atoms is determined by a number of photons, and we are interested in the atoms very high in the atmosphere, there is less photons because now they are escaping, and the levels are starting to become underpopulated. And what happens is that I have less emission in the line, and that's why the lines become so deep. So basically, the reason why sodium lines are so deep is that for some reason, their emission drops below their, let's say, predicted emission or whatever. And I'm actually going to show up a little bit later the differences between these things. Okay, so that's all good and fine, and we have these lines, and they're in non-LTE, but what happens with their polarization? As you have noticed already a few times, I have shown you that I'm not only interested in the intensity of these lines, or we are not only interested in the intensity of these lines, but also the polarization state there. So apparently, as we can see from, yeah, I'm sorry, I probably forgot to turn on the animation effects here, but you still can see here the intensity Stokes U and Stokes V in example Hinode spectra, and here you can see intensity and Stokes V in example of the spectra that we are analyzing. And for some reason, there is polarization here. The physics in this is relatively complicated, and here is just a little refresher on what we mean by I, Q, U, and V. So basically, I tells you the total intensity of polarization, Q and U uniquely determine the linear polarization state, and V tells you the circular polarization. And the three main sort of contributors or three main causes for the polarization in spectral lines are Zeeman effect, scattering polarization, and Hanle effect, which basically depends on both, let's call it geometry or anisotropy, and the magnetic field. But here we are going to be focusing on Zeeman effect. And usually when people say Zeeman effect, what we remember from the undergrads, for example, is that it's splitting of the energy levels because of the presence of the magnetic field. And that's how we know from the observations of HAO that there are magnetic fields in the sunspots. Right. However, it's not immediately obvious why would atoms permitted by magnetic field emit polarized light. Actually, in case of Zeeman effect, they're not emitting polarized light, they're modifying the state of the polarization. And what happens here, and this is very basic scheme, is if we consider just the simplest possible case of Zeeman splitting, when the lower level is unsplit and the upper level has total angular momentum 1, so it's split in 3 sublevels, we have basically 3 subtransitions. So one line turns into 3 transitions. However, depending on the direction that you're looking at, and let's say, for example, that you're looking along the magnetic field, the only transitions permitted along this ray are going to be the transitions from 1 to 0 here and from -1 to 0 here. And the reason for this is actually the law of conservation of angular momentum in the atom. It's not immediately clear why is it so, and we can discuss later in the details, but that's actually what's happening. So we only see these 2 sigma transitions. We usually call them sigma blue and sigma red. And when you look on the level of photons, each photon is basically circularly polarized in one or the other direction. So what we see here are the 2 transitions which result in circularly polarized photons. But now, because there is shift in energy, so still keep in mind that they are also split, their energies are also split, which means their wavelengths are split, I get sort of this thing, that they would cancel each other if there was no energy degeneracy, but now I shift their energies a little bit, which means I shift their wavelengths a little bit, and I get this characteristic antisymmetric Stokes V profile here. And then if we look perpendicular to the magnetic field, situation becomes more complicated. We see all three transitions, but now in a way we see projections of these. So we also see them as linearly polarized, but we also see the pi transition, which is from 0 to 0, and then it has this sort of characteristic profile for Q and U. And in practice, in the modeling way, what we actually have to do is we need to calculate these effects for each point in the solar atmosphere, and then again solve radiative transfer equation, but this case for polarized light. And it now becomes basically a differential vector equation, which is, again, looks a bit scary, and the magnetic field and the atomic constants go in all these elements of this absorption matrix here. But we have, again, today very efficient and relatively straightforward numerical ways to solve this. So eventually, we know how to model these things. If you give us model, let's say MHD model, we can calculate intensity and Zeeman polarization, et cetera, But the question comes how to do the inverse thing. So this was the forward problem all this time. How do we solve the inverse problem? Because what we have are these polarized spectra, and we want to interpret them. And this is basically this field or this method to do this. We call it spectral polarimetric inversion. And this is the method of fitting your chosen model atmosphere to the observed polarized spectra. And you hope that by obtaining a good fit, that you can say, okay, if this atmosphere fits this spectra very well, now I can say that what I'm actually seeing, that the atmosphere underneath responsible for this spectra is this, what I fit. Okay, and basically this is how inversions work. So this is a very simple toy model of some non-LTE line, doesn't matter much. And here in these 4 panels, you can see I, Q, U, V, and you can see how the red line, which is our guess model, is adjusting and trying to find a good fit, and the blue lines are the synthetic observations, let's say. Here you see how our merit function, which is in this case chi-square, how it is slowly going down through a number of iterations. And here we actually see what inversion scheme is doing. And in this case, the only thing that I'm plotting is how the temperature stratification is changing with iterations, trying to find the best fit here. But of course, we are not only changing the temperature stratification, we are also changing the other parameters. Just for the clarity, I wanted to show all this one. However, usually when people plot you like temperature stratification or velocity stratification or something else, it looks very continuous and nice. But in practice, to really independently deduce each of these or infer the value of each of these points here, it's very hard because the problem is very degenerate. And we could speak about it for long time. Basically, what we want to do in practice and what people practically do in practice is they say, okay, I can't really infer all this structure uniquely. What I'm going to do is I'm going to reduce its structure to be determined by these 5 points here, or 6 or 7 or 12 or 15, and we call these points nodes. And this is what people mean when they say node-based inversion. And that basically means that I have simplified my atmosphere by using these nodes and assuming that, for example, in between they need to follow some, let's say, spline stratification or something like that. And what you might have guessed before is that this fitting has to be based on some minimization scheme. And that's actually what we do. And most efficient minimization schemes are usually ones based on derivatives. And what you usually want to have in a minimization scheme is the derivative of your observable with respect to your model parameters. And we can calculate these things in spectropolarimetry, and they're very useful, and they're called response functions. And here I'm showing a sort of pragmatic form of the source function, where basically what I'm plotting, I don't know if, yeah, what I'm showing is the derivative of the emergent intensity at various wavelengths with respect to temperature at various depths. And so usually a response function is this sort of surface plot. And what you see here is the response function of these widely used Hinode lines. And you see here something that most of you probably already intuitively know, and that is that at continuum wavelengths, the radiation is mostly sensitive to the layers around log tau 0, which we usually call photosphere. But then as we go towards the core of the central lines, the sensitivity regions move higher and higher. So that is why, for example, with Hinode lines, we can diagnose the layers from 0 up to maybe log tau minus 3 or so. And now I can plot these for my sodium line. And if you calculated sodium line naively using the absorption of LTE, you would get wrong line profile. And you would also get the impression that your sensitivity is very high, so up to -4 or even -5. But that's not true because sodium is a non-LTE line. So when we do this calculation properly, not only does the line shape change to something that you are used to, but also the response function changes. So I want you to pay attention to this. So my sensitivity region moved down, right? So I lost all this sensitivity up there, and it went down here. Why is it so? Well, it is so specifically because of this non-locality that I spoke about before. What happens here, and we also see this in H alpha, is that the lower regions, because the line is in non-LTE, it is scattering line. The regions up there in the chromosphere, let's say, where the line is formed, the population of the atomic levels there, it's not determined by the local quantities. It's determined by the radiation that is coming from below. So if I change the temperature locally up there, maybe I'm going to make my line a little bit narrower or a little bit wider. But the actual intensity, the actual populations of the atoms, I can change only by tuning the temperature down there. And in this case, it's this region just below the temperature minimum here. And this is actually, when I discuss this with Rafa, he usually says, "No, but it's beautiful. It means that you don't have to worry about these regions up here. So you can model your line much more easy," which is, of course, a joking way of saying it, but it basically means that the sodium line cannot tell us anything about the temperatures up here. Probably. Okay. I mean, keep in mind that this is calculated from one model of the atmosphere. This is calculation from FAL-C model, which we all use when we want to learn something about specific spectral line. When this changes depending on the atomic model. So if I did this for a plage or a sunspot or, I don't know, some hot region, it would look differently. Okay, but it's good to just see these effects. And now we can plot these for various Stokes components and for various quantities. So we already have seen how it looks for Stokes psi and the temperature, but the things are going to look different if I calculate response functions to magnetic field, for example. And I sort of should have reduced the wavelength range here, but it's also good to have it like this to stress that in the case of intensity and the temperature, basically your whole spectrum is sensitive to temperature. Continuum at least gives you some information of the temperature in the photosphere. But if we want to infer magnetic field and velocity, we really need the spectral lines. So because the spectral lines are the only features in the spectra that are sensitive to these things. And what you also can see here, and usually I'm going to focus on Stokes V, is that actually when we talk about Stokes V and the magnetic field, sodium line is sensitive to much higher regions. Now these can also be misleading, because you can see that all this upper region responds more or less the same to the magnetic field. So if I increase my magnetic field here and I decrease it by the same amount here, my emergent profile is going to be more or less the same. So these are sort of degenerate regions. So in principle, even though this response function spans nicely all the way from tau minus 1 to tau minus 5, I might have more or less only two regimes to analyze, so to speak. I have this line core, which responds more or less in the same way, and I have these diffuse wings. So in principle, I maybe could just infer two values of the magnetic field, and actually, as you will see, that's what I'm going to do. And then you can do the same for the line of sight velocity, et cetera, et cetera. So that we see where our line is sensitive to. Very good. So I spent most of my time in MPS actually finding efficient ways to calculate these response functions and then developing a code based on them. And that's what Michiel and me did. And we developed this code called SNAPPy, which is an acronym for Spectropolarimetric Non-LTE Analytically Powered Inversion, because apparently acronyms are very important. And we also use this node-based approach. Also, hopefully, with future developments, we might be able to abandon it. And here is the example. So instead of really treating all this stratification, you only sort of discretize your temperature dependence by using these 4 discrete points, or magnetic field dependence by using 2 points, et cetera, et cetera.
And you are doing this at this center?
These observations are at this center, but you can do this wherever you want. But in principle, if you were going to look at limb, then your sensitivity is going to change, right? You're going to be more sensitive to shallow layers and less to the deep layers, because you're looking.
Also changes, of course, your inversion problem.
Yes, because you're looking at the atmosphere like this. Yes, yes, yes. True. So let's go back to these observations. I didn't mention this, but this is the application of this spectral reconstruction technique, which Michiel developed, which is based on not really slowly, which is based on continuously scanning with a slit, and then you use the context observation from a different camera, which is connected to just basically continuum image, which gives you information about your spatial PSF. And then you use the spatial PSF that you infer by reconstructing these continuum images, you use them to reconstruct the spectra. So what you get, I'm sorry for this, my new Ubuntu is messing up the video. So basically what you get is then you can get basically almost diffraction limited observations with this super nice spectral resolution, but sadly your noise is relatively large. And noise in this observation is like 1%, which sounds little, but is actually very, very big when you want to do precise polarimetry. Right. And here is what you would get if you applied these inversion methods on this data. This is only the half of the field of view because it makes all the images fit very nicely, but this is what I want to call inversion results in one slide. So basically, let's spend some time discussing what we have here. And in the top 2 panels, we have continuum intensity and circular Stokes V close to the line center of sodium D1 line. So you see here basically that now your intensity image agrees rather well with the inferred temperature at the photosphere, which is something that you would expect, and that your Stokes V resembles, at least the distribution resembles the distribution of the magnetic field. But you see here that and for those of you who are not familiar with what log tau equals blah, blah, blah is, these basically denote, so we can't really use height here. I can't say, okay, I have magnetic field at 0 kilometers, which is this big, and then 200 kilometers this big, and 300 kilometers this big, because spectra doesn't care of this. All the radiative transfer, all the spectra formation, it happens on the optical depth scale. So in radiative transfer, we always use optical depth as our independent quantity. And in some canonical model atmosphere, as for example Fal C, you would have photosphere at log tau 0, you would have inverse granulation at log tau -1, temperature minimum at log tau -3, and then chromosphere, and so on and so on. But these things change in the spatially resolved observations. These things change context in a way. Okay. But what we have here, so I'm here plotting basically the results, the values of the quantities in the nodes that I have used. So here we have the temperature at the photosphere, and that is more or less straightforward. Then we have a temperature in the upper layer. In this case, it's log tau -0.7. And you see here nicely the plage and the inverse granulation and so. And then when you look at the velocity, you see that at log tau minus 0.5, which is photosphere, you see the characteristic signature of the granulation. But then when you go to upper layers, which is something close to the temperature minimum, you see completely different signature of velocity. And then again for the magnetic field, these two regimes look similar, but you see that in the upper layers, the magnetic field is weaker and more diffuse. And this is the signature of we often tend to call canopy, which or if you want to call it expansion of the flux tubes, that as you go up in the atmosphere, the flux tubes become more wide, but also magnetic field in them is more weak. And it would be super nice if we could complement this with some linear polarization observations. And sadly, I mean, of course we have them, but the noise is simply too high to deduce anything, because linear polarization could exactly tell you how the inclination of your magnetic field is changing, and you could really reconstruct the shape of this magnetic canopy. Okay, so this is nice, and we can discuss maybe after the talk more about what actually physics is hiding in there, but my interest is always the inference method as it is, and it's very nice. These are very nice maps, but we should always be worried what is happening here, because as this dog is saying, it's question who is conditioning who here. So we have nice fits, but is it really the physics that is hiding behind the observations, right? So this is now the same thing. So as I said, I'm only showing you the half of the observed field of view. And there were two reasons for this. One is that this looks nicer when I pack them, at least to me, when I pack them like this. The other one was that I was in for an interesting surprise, because due to the huge memory required to store these things, I had to invert these maps in 2 goes. So then this would be the magnetic field for the whole observed field of view, right? And you can see that somehow this lower part of the picture here looks somehow sharper. And then I thought, okay, it's very unlikely that there is some selective observational effect or something like that. So what happened with these? And then I realized that I actually started the inversion in these 2 different pieces of the map with 2 different initializations, 2 different initial conditions. And in principle, these should converge to the same minima. But then by analyzing various other physical quantities, I noticed that it's not the case. And this is a particularly nasty one. This is the map of microturbulent velocity, which is something that we all use in order to explain missing line width. And in spectropolarimetric inversions, we still use them almost for all the lines. But as you can see here, these things caused me a little bit of a problem. Because these 2 maps, due to the fact they were initiated from different initial conditions, converged to do 2 different solutions. And these 2 different solutions had equally good merit function, so the fits were equally good. And until I plotted these maps of quantities, I couldn't see what the thing was. And actually, the microturbulent velocity here is significantly lower than up here. And then, of course, what I did is that I simply restarted the whole process and things converged. But I still can't tell you which is the correct thing. And I can't even tell you whether this quantity here is needed, because now I have another set of these inversions with microturbulent velocity turned off. And these, again, give you some nice fits. We can debate whether they're better or worse. I mean, they're slightly worse, but you are also eliminating one whole physical parameter. So you are somehow simplifying your model significantly. So I think it would be really nice if we could put some effort and settle, maybe not once and for all, but at least settle a little bit better issue whether microturbulence exists. Some of the people who I know really don't believe that microturbulence exists when you look at the high resolution observations. Some people think it still exists because it happens on super small scales. So it's an interesting question, and if you have some feedback, I'd be happy to hear it. So that's like the challenge number 1, uniqueness. And it doesn't only happen in this case, and it actually also happens within one and the same parameter, that you simply can't infer your quantity very, very well. So these are sort of Markov chain Monte Carlo tests of inversion of calcium 8542 line, done by Carlos José Díaz Basso from University of Stockholm. And so he's inverting here one single calcium line profile, and what I'm showing you here is basically the uncertainty in the inferred model atmospheres. So you see here that, for example, calcium infrared line gives you very well this piece of the atmosphere here. And there is this one point here, which is very well constrained. But then when you go to upper regions and this intermediate region here, you are very poorly constrained. So you might get for two very similar profiles, two very different model atmospheres. So you need to know your line and its behavior in different regimes in order to have faith in your inversion results or no. And then what we want to do now is we want to study these sort of things, but as correlations between different parameters. Okay, and this is very numerically demanding, because to do an MCMC study, you need to evaluate many times the forward problem, and non-LTE problem is computationally demanding, right? But another problem is that to interpret this huge amount of data, what I showed you before was like 600 times 1,000 pixel map, so some order of 1 million profiles. To invert it, it takes a lot of time. So if, let's say that we had an inversion scheme for a non-LTE line which took 1 second per iteration, which doesn't mean anything to you, but I can tell you that it's very little. We are doing much worse today. And you needed only 10 iterations to fit your profile. And you wanted to fit the million times million pixel fields. It means that you need to do 10 million iterations of 1 second each, which is 100 days on one computer, or 1 day on 100 processors. And although 100 processors doesn't sound so little, it's also not super trivial to have an efficient parallelized code working on 100 processors. And this is only for one observed field of view, right? We know that, for example, with IBIS, you can get thousands of spectroscopic cubes in 1 day, right? And with DKIST, we're probably going to have what? 4K times 4K, and then who knows how much of these. So it's going to be a huge amount of data. And to invert all that, it's going to take a lot of time. But the things that we observe are very similar. So you see here that, like when you look at this image, here, what? We have granule, intergranule, plage. Like, things are similar among themselves. It's not like I have infinite information in this image here. It's just how it is distributed. So what we can maybe do, and some people are doing, and I'm going to show you some preliminary results, is that we could, in principle, train a neural network to do this for us. And people are doing it now in other fields. So people are doing it, for example, for quasar spectra, and in solar physics, people are doing it for some other things, like to use it instead of correlation tracking, to do very fast blind deconvolution and things like that. But for inversions, it's still starting. And what would I say that we could do, for example, is that, what is a neural network? So it's basically a very simple sequence of linear operations, which eventually takes your input and turns it into output. Then you give it a set of inputs and outputs, and then the neural network tunes these parameters of these linear transformations in between until it finds the best agreement between the input and output, so to speak. Okay. And in principle, you can think about it as a very clever way to do interpolation, or a very clever way to approximate the mapping between input and output that you have. So what I did in the following slides is I took a middle segment of this observed cube, and I performed inversions there until I was happy with the results, and then I trained my neural network on these results. So basically what I input there was the polarized spectra, and what was the output were these physical parameters, or these values at the nodes. So I tried to have in this piece of the cube representative of everything. So a bit of plage, a bit of quiet sun, etc., etc. Then I train it on this subset of the data, and I apply it to the whole data. And the results look rather nice. So now I'm showing you basically the same thing as before. So I'm just going to run through it, except now you see the full field of view that we have. So this is the temperature. This is the velocity. What I would like to take a better look at are these velocity signatures in the upper atmosphere, which correspond to where the plage is, and I want to see why do they look like that and how the velocity behaves there. And then also for the magnetic field, we have this. We see this canopy effect and fanning out, and now you see that there is no this regime here because the neural network was trained on one consistent set of results, so it's sort of giving out the results. And now the question is, of course, how does this compare to actual inversion? So then what I did, so I admit I didn't do it from the start, I just gave inversion this as starting conditions and try to see how much it can improve of this. And the actual result is not much. So these are the comparisons now between the whole field of view, between what the neural network is giving, and it doesn't really matter which is which because they look completely identical. But what you should pay attention to are the histograms of the differences. So these are the differences, and they are really, really small. So for this layer here, the sigma is what? Like 100 Kelvin. Here maybe 50 Kelvin. And then for the velocity, the differences are also super small. And also for the magnetic field. So basically, the neural network is really capable of capturing from this middle picture here, basically interpolating what should be expected results in the rest of the field. So I want to stress that, I mean, you will probably hear from other people in the near future different approaches to this, and the agreement is remarkable, but this is really because I'm only training the network to do what my inversion is already doing. So I'm not relying on any simulations. I really just want to say, okay, I have this representative set of data, take this data, learn on this data, and give me what should be the answers for the rest of the data. And this is some sort of, we could call it, data-driven approach. So there are some people who are doing this on MHD models, which is good in one way because they contain the physics, but is also bad in another way because you only see what MHD models are giving you. And the main advantage of the neural networks is that they are extremely fast. And I'm actually not the first person to notice that, far from that. If you read Luis's review on inversions from 2006, he says there explicitly the sentence, neural network will invert the whole field of view in a matter of seconds. And it's really true. So you really get something that you will never ever be able to achieve with any minimization method. Because it's really, once you train it, it's really just set of few linear operations applied to your spectra, and you get the answer. And in principle, what we are doing here is sort of, we are mimicking what inversion is doing and just quickly extrapolating it for the rest of data. And that's everything that I had for today. Thank you very much.
Thank you, Ivan. Questions? Matthias?
Just a question about the neural network. Did you train it to essentially do a pixel by pixel inversion?
Yes.
Or did you train it in a way that it actually learns something about the neighborhood of pixels and takes that information into?
That's a great question. It's just pixel by pixel, but it still gives very smooth images.
Yeah.
And my interpretation is that basically when we see images, when we do inversions and we see this salt and pepper usually results either from the fact that you got stuck in some local minima somewhere, or your specific noise realization was such that when you fit it, you end it in significantly different solutions. But somehow, since network is trying to learn this mapping, it can sort of ignore these things in between. So you still get very, very smooth output. But one option to do what you want, what you are asking, would be to teach on segments, and then you could, for example, enforce div b equals 0 or something like that. And that would really improve significantly the things that we're doing.
Mark. So while you're on this slide, this quantity, particularly on the right, the magnetic field, is the only one where there seems to be a systematic difference between the neural network and the inversion. That's not a symmetric distribution.
To really, you're probably true, and there is probably something, and I think it is because the neural, in principle, these inversions have also inclination as free parameter. And the inclination is, in principle, you should be able to, although to really get inclination, you should get linear polarization. But in theory, you should be able to infer it only from the intensity and circular polarization because the shape of the line is influenced by that. And it seems that my neural network scheme can't really pick it up very well. And to really see this better, we would have to, I really plotted this very poorly because I admit I did it this morning. We would have to remove the basically pixels where our magnetic field is 0 and then to analyze these distributions. But you're right, there is some offset. But I mean, keep in mind that this is offset of what, maybe 20, 30 Gauss, and these fields are like 1,000 Gauss or so. So I don't think that people would complain too much.
No, it's just striking because your temperature, your other variables are all symmetric. So if it's just learning what you did in the inversion,
it shouldn't be biased.
It shouldn't be biased.
Yeah, but to really answer that question, I would have to really train it much more carefully. So, for example, we should repeat it on, for example, learn on this half of the image and then see how this behaves, and then learn on this half of the image, see how this half behaves, and so on to see if this problem persists. Because when you take, for example, central, here I took like 40,000 pixels, I think, you are not 100% sure that it's really representative of the whole. So, I mean, I'm also guessing. I didn't check. So we should look into it. Okay.
Microturbulence degeneracy compensates exclusively with the temperature.
I think it compensates with everything, because what you see here is its influence on the magnetic field. So it's also compensating for the because magnetic field broadens the line a bit, and so does the microturbulence. But then it also it's really terrible because if you have a depth-dependent velocity, that can broaden your line. If you have temperature, that can broaden your line, and then you have magnetic field, which broadens your line, and then on top of that, you have microturbulent velocity, which broadens your line. So it's really terrible. And I prefer, if possible, not to use it at all. But what do you know?
I mean, related to this question, I mean, have people tried to estimate, for example, doing these sort of inversion on actually simulation data, whether not using microturbulence actually leads to a better agreement with the ground truth in that case? I mean, sometimes microturbulence helps you to better reproduce your spectrum, but the question is, do you better reproduce the physical state?
Yes, that's a very good question. I did it in, we didn't really focus on microturbulence. We did it just recently. I did it with Smitha and Andreas. And you usually, for some reason, when you invert the synthetic data, you get better fits when you use microturbulence. And it sort of just helps you to account for the depth variation of the things. But to really study that, what you should do is you should have very simple stratifications for temperature, magnetic field, and everything except velocity, and then study that. Because I did literally what you suggested, and my velocity is very well recovered in both cases. Microturbulence gives you some better fits, but then when you plot the plot of microturbulence, you can't really see what it correlates with. So it's really, we really have to make sort of synthetic models to really isolate and see what the microturbulence compensates for. Like if I have, to say it better, I need to have like an MHD simulation or pseudo-MHD simulation, something resulting from MHD simulation where my temperature structure is very simple so that my inversion, scheme can exactly reproduce it, and literally just fit and say, okay, now I'm fitting only the velocity basically. And I see what microturbulence compensates for. Then I say, okay, I fix everything else. I'm fitting only for the temperature. Let's see what microturbulence compensates for, and so on. And it sounds like, why don't you guys do it 10 years ago? But it's really not trivial. It's really, really tricky. I mean, even inverting synthetic data is not always easy.
What do you do with fill factors? Anything?
We don't use filling factors here. We could do them.
Resolution.
This is like 0.1 arc seconds. Yeah. So you could use filling factors, and I think that for this sort of noise, you can't really say whether you need filling factor. I mean, it also depends on what do you mean by filling factor. Do you mean filling factor to account for the stray light of the instrument, or truly filling factor?
Let's see, the Stokes inversion gives you the average field in
Yes.
your resolution element.
Yep.
Now, that's the average field.
Mm-hmm.
And the flux you get by multiplying that by the area.
Yeah.
But now, where is the flux?
Exactly. I mean, in principle, if you had very good observations, you should be able to discern between these two things, because the magnitude of Stokes V will be same in the case of high magnetic field and low filling factor, and low magnetic field and high filling factor, but the exact shape of the line will not, right? So you should, but here you can't say it. So I prefer just to say my mean magnetic field is this. There could be filling factor, or there could be not. Because in principle, we should be able, if we had really accurate observations, we should be able to also infer the filling factor as such. And some people have done it.
Any more questions? Ricky?
Anything interesting about the tails of the distribution of differences between your neural network and the minimization inversion? Because I wonder if there's things like if you train the network on some set of observations and then you have outlying pixels that are doing interesting physical things.
Oh, yeah.
Is that where the differences are?
Yeah, here I don't think so, but in principle, yes. And that's what we also need to be, I mean, I was going to advocate for this, for like Dickist or something like that, but you also want to look for the data, for the interesting data. And I don't think that here in the wings there is that, but in principle you could find it, especially when you want to study some time dependence. Like it could be that something just happens, something explodes, some shock is created, and your neural network doesn't know what to do with it. So we still need the methods which will very quickly interpret what is common and known, but also point us to these interesting things. Because neural network is great if I just want to estimate total magnetic flux in the image, right? If there is one pixel where something weird is happening, it doesn't influence my things. But to interpret these things, we still have to do it by hand, I think.
All right.
Does quality control something like taking the inversion from the neural network, synthesizing, comparing to observations, and using that as...
Yeah, you could. I mean, in principle...
But there's a lot of disparity, then you're like, okay, this is a place where...
Yes, in principle, you would have to have a pipeline which has a neural network as a quick neural network as estimation. Then it synthesizes the line profile from what neural network tells it, compares it to the observed one. If the agreement is satisfactory, it does nothing. And then if it's not satisfactory, it starts the inversion until it reaches what it needs. So that would be, but that's not trivial to develop.
All right, I think we're going to end the discussion there.
Sure.
Ivan will be around for another 2 years, 10 months or so.
Yeah.
So if you want to discuss with him, then shoot him an email.
Yeah.
All right, thanks, Ivan.
You're welcome.